All right, so we're going to look at 7-6 quadratic functions. So the form that you already know is vertex form. Okay, and you've seen this, and your book calls it completed square form. That's why it's in parentheses there. But if you remember, this really looked like this. Okay? And that's the exact same thing. How do we know it's the same thing? F of x is really y. And then what happens to the k, Manor? Yeah, you just subtract it over. So these are identical. All right? So the book calls it completed square form. I call it vertex form. I've seen it as vertex form now. You'll see it online when you look it up as vertex form. So I want you to be able to look that up. Completed square form doesn't really show up for this name. The book is an old book, but it's a really good book that you guys use. It really is. It's just some of the terms are a little outdated, so I try to give you more of a up-to-date look. Anyhow, standard form is just your simple quadratic form. Okay? Everybody good on that? Now, first example says, determine the vertex and axis of symmetry of the following function by transforming it to vertex form. So we're going to use completing the square to get it back to vertex form. It'll look like this eventually, and I'll show you the steps. And then we're going to find out what the axis of symmetry is. Then what we're going to do is take a look back at the original up here, back at the original, and what we're going to say is we're going to look at negative b, so the opposite of this, over 2a, and get an answer and show that they're the same. And from that point on, we'll be able to use this formula whenever we're finding the axis of symmetry. Okay? This is the formula you're going to use to find the axis of symmetry instead of x equals h, which is what we've used from here. See, this h value turns out to be 2 here, and that's what the axis is. Well, if you look at negative b over 2a, you're also going to get 2. And that's a little bit of a correlation we're going to see. And we're going to be able to use this formula from now on. Okay? So we don't have to transform. So the process I'm showing you now, you're not going to have to do again. Okay? We're just using this process to prove that this is true. And then from this point on, we'll use the fact that x equals negative b over 2a to determine the axis of symmetry. Okay? The board is lagging a little, I know. It's on my point, okay? So, the way it's done is by looking at the original here. Now remember, you're always going to move the c value over, but now we don't have 0 over here, so it becomes y minus 7. And we're left with this quantity. Now, remember we would divide by a normally. So take a look here. I'm going to underline what I want you to be looking at right now. Okay? We normally divide the whole thing by a, but that would divide y by 3, which we don't want to do. So instead of dividing by 3, we factor out whatever the a value is. When you factor a 3 out of here, remember, just divide the 12 by 3, and that's where the 4 gets its value. So now take a look at this quantity right here. Complete the square. Take half of b, which is negative 2. Look at the board when I talk. Take half of b, which is negative 2, square it and add it inside of here. So half of that is negative 2, squared is 4. So you're adding a 4 in here, but remember that there's a 3 as a multiplier on the outside. So you're not just adding 4, but you're adding 12. If you were to redistribute this 3, that's really a 12. So you need to add 12 to this side over here. That's where that 12 comes from. So now on this side, you have this quantity, negative 7 plus 12, which is just 5. And what you've done is you've created this perfect square over here, which can be factored into x minus 2, x minus 2. And that's where this x minus 2 quantity squared comes from. And now it's in vertex form. And take a look. The k value is negative 5 from here, and the h value is positive 2 from here. So here's k. It's negative 5. It's the opposite of that, remember, because it's y minus k. And this is x minus h, so h is just that 2. The a value, not that it matters though, is a 3. And notice the a value is consistent in both forms here. It doesn't change. But the h and k is here, and now the b and the c are over here. What we can do, though, is look at x equals negative b over 2a. X equals negative b, so negative 12. Come on. There we go. All over 2a. All right? So we're going to get positive 12 over 6, which is 2. So we get an axis of symmetry of 2 by using negative b over 2a. But take a look. This is the axis of symmetry. Remember, the axis is x equals h, which means it's just x equals 2. So either way, the axis of symmetry is x equals 2. So we can always use the vertex form and get the axis by looking there, but we could also just go ahead and take a look at negative b over 2a. Now, one second, Alejandro. The next part is that we know the vertex is hk. So the vertex is 2, -5. But what you'll notice is that if we just take the 2 and plug it into the standard form at the top, we'll get -5, the vertex. Take a look. Plug a 2 up here. So again, what am I doing? I'm plugging in 2 into this equation up here. And I'll write it in blue. And I should really, to be safe, put the square on the outside. Because if this were a negative number, I have to remember negative squared is a positive. So I should really write it like that. 2 squared is 4, times 3 is 12. 12 times 7, or 12 times 2, sorry, is 24. Plus 7. Did I write it wrong? We're going to get 19 minus 24 is -5. Sorry, I was looking at it differently. Okay? So either way, when you plug the vertex or the axis symmetry back into the original form in standard form, you'll get the vertex. Or if you look at h comma k, you'll also get the vertex.
So to find the axis symmetry, you plug in the A, B, and C of the original.
Correct. And you use -b over 2a. And what do you notice? Anybody recall where this comes from, -b over 2a? Where have you seen that term before? That's very good, Manny. That's exactly right. It's in the quadratic formula. So if you think back to the quadratic formula, let's do this. Can we erase the whole thing? Yeah. All right. If you look back at the quadratic formula, you'll remember x equals -b plus or minus square root of b squared minus 4ac all over 2a. If this is just 0, if the discriminant is 0, this drops off, right? And what are you left with? -b over 2a. So when the discriminant is 0, that's the example of the graph that looked like this, where it was tangent to the graph. And take a look. When the discriminant is 0, the axis of symmetry is right through the vertex, and the vertex is on the x-axis because the discriminant is 0. So there's your -b over 2a because the discriminant is 0. That's one of our exceptional cases.
Is it possible for A to be 0?
For a to be 0, what kind of a function would you have if a was 0? Not undefined. It would be bx plus c, wouldn't it? Take a look, Nick. Standard form back up here. Drop a off. What are you left with? Isn't it bx plus c?
Yeah.
What kind of a function is that?
A standard?
Another term. Not standard, use a better word for that. It's a standard form of a... No, bx plus c. There's no square term anymore. So what kind of a function is it?
A normal function.
Okay. Linear. Ax plus b. Isn't that a linear function? Remember? Linear functions follow the form ax plus b, or we call it mx plus b, where m is a constant and b is a constant. Well, bx plus c is the same thing as mx plus b, just different coefficient variables. The b is now the m, the c is now the b. Who cares? They're dummies. You know what dummies mean in math? For real. It's not like... No. Real term. Not similar, but replaceable. I could call it box. I could call it triangle. It's a variable. It's a dummy variable. It can be replaced by anything. It doesn't matter. So in this case, if you drop a, you get a linear function. That's a good comment. I'm glad you asked. Because nobody's asked that yet. Maybe other people saw that right away. Maybe it was something that you didn't want to ask right away. But either way, it was a good question. Okay? Very good. So let's take a look at the second example here. We have given that this is the function, find the following. And this, I think, was a tough problem for some people when they were looking at the notes. Okay? So we want the vertex first. And remember, find the axis, plug it back into the original, and you'll get the vertex like we showed. So let's find the axis. X equals -b over 2a is the axis. Negative, and b is 4, c is 3, and a is -1, because this is not in the right order. So -b over 2a is -4 over -2, which is 2. If you take 2 and plug it into g up here, you get 3 plus 8, which is 11, minus 4, which gives you 7. So the axis is 2. When you plug it in, you get 7, so the vertex is 2, 7. Yes? Next, the domain of g. What does domain mean again? What did we talk about when we said domain and range? What was domain?
Domain was with all the values of x.
All the values of x. Go ahead, sorry.
And range was y.
Yeah, and range was all the values of y. So Mike, tell me, if you pick any value for x, are you going to get out some value for g of x or for y? Do you get an answer? Yeah. I mean, pick any number. It doesn't matter what you pick for x. You can pick any value. And you can also look at the shape of a parabola. This parabola looks like the following. 2, 7 is here. Okay? The y-intercept I know is here, and I'll talk about that in a minute. But the y-intercept doesn't really indicate too much, but the vertex tells me 2, 7, so I'm on this side. Well, take a look. These have arrows on the ends of them. What do those arrows mean? Johnny? Yeah, it continues. And Johnny, isn't this at an angle? Yeah, so it's going to go on down forever. And it's also going to go to the left forever. And it's going to go to the right forever. So it extends forever left and extends forever to the right. And the domain is left to right, or the x values, isn't it? So the domain is all real numbers. You can think of it graphically. You can think of it like, all right, what number can I plug in for x? Any number can. But what about the range? Who's got the keen sense here and knows what's going on with the range? It's a little different, right? It's a little different.
I was going to say, it depends on like what the domain is first.
Okay, but look at the graph, Summer.
It's going to be negative then?
Everything's going down, but what's the highest point, Summer, on the graph? In the y? 7. But nothing is above 7, right? Everything is down, like she said. Everything is going to be negative from there. So everything is less than or equal to 7. Okay? All right? All real numbers less than or equal to 7. This is because a is negative, so the parabola opens down. What if a were positive and the parabola opened up? It would be all numbers not less than 7, greater than 7. Because the parabola opens up. Is this clear? This is very important that you get this.
No, I represent anything you said.
So look at the maximum point. On A?
Yeah.
What's the issue with A? Quick.
Plugging 2,
Uh-huh.
negative 2, or just 2 and then you multiply.
When you plug in 2 into the function, you get 7.
Yeah, but when you plug in the 2 for x,
Mm-hmm.
does it become negative 2 squared?
No. It's minus 2 squared. So it's minus 4. Remember, Alejandro, take a look. That's what it looks like. Take a look up here, please. Right? The minus sign is a minus sign. It's not a negative sign. There is no negative number being squared here. If it was g of negative 2, it would be a negative square. Okay? So that's where the 7 comes from. Then we go on to the domain. And the domain says any number in the x, because this extends infinitely to the left, infinitely to the right. Or we could say, plug in any value of x. You get a value for y. So any number can go in for x. So the domain is all real numbers. And then for part C, we look at the vertex limits the y values. Nothing is above 7. So it's all real numbers less than or equal to 7. That's because a is negative. If a were positive, it'd be all real numbers greater than 7. Okay? Katarina?
Would there be any occasion in which the domain would not be all real numbers?
Sure, different types of functions. So a square root function, its graph looks like this. And the domain is every number greater than 0. Because you can't have a negative under the square root, or else the number is imaginary. And we're graphing on the real plane. There's something called the complex plane, which is different. And if you go on to higher levels of calculus, you'll graph on there. And it's not tough. Just the axis along this way has an eye on it. So any imaginary number gets plotted there. It's real easy. So don't worry about it. But for now, just know that the domain can vary based on the function type. Okay? So anyhow, the fourth part was D. It said find the zeros. What are the zeros of a function? Katarina? The roots. So you go to the quadratic formula, you use the quadratic formula, and you get the roots. Now, if I were to graph this, would I leave my roots like that? What would I do with them? Show the what representation? Fill in the blank. Good. The decimal representation. Because if I'm graphing, where the heck is 2 plus root 7, Summer? Any idea where that is really? No, it's 2, and then it's a few units over. Something between 2 and 3 more units over. Because 7 is between 4 and 9, and those are perfect squares. But it doesn't help me too much. So show the decimal, please. Intercepts, I just wanted to reiterate. I'm not going to go over that again. But remember that when the domain, because we're talking about domain, see that? When the discriminant is positive, you get 2 answers. So that's 2x intercepts. When the discriminant is 0, you get 1 repeated root. That's this root right here. It's repeated, it's tangent. When the discriminant is negative, the roots are imaginary, so they don't show up. So there's no x-intercepts when the discriminant is negative. Okay? A reiteration of what we already said. Next is extrema. Here's the important part of this lesson. Okay, this is the most important part. This is something you'll take on with you to calculus. And the term extrema is not even taught in your book. I've used it. Actually, in your book might use it. They might. I don't know. But a lot of people don't use extrema until calculus. It's the same thing. Extrema, what does that word sound like to you? Extreme. Extreme means really, 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 like a high score on a test or a really, really low score on a test. Aren't those extreme scores? So extrema are mins and maxes for that reason. So when a minimum appears, it means that the graph, is opening up. Right? Think about it. Look at the shape of this graph. The minimum is like the valley. It's the low point. When you're at a minimum, you're at a low in life. When you're at a maximum, you're at a high in life. It means you're very happy. Things are going your way. The maximum is when the graph opens down and you're at like a peak, like the top of a hill. Okay? And I talked about this, and I told you guys about engineering, how this is called a stable point, because if you drop imagine you drop a marble, it's going to teeter out in that point. But if you put a marble at the top, any movement will cause it to do what? Fall off. So I called this an unstable point. But what you need to know for the idea in math is that this is a max and this is a min. Okay? And you'll notice that they're the vertexes. The vertices are maxes and mins, respectively. Each graph that is a parabola will have either a max or a min. If you had a graph like this, though, and somebody asked this in the other class, you have what are called local maxes and mins. This is a local max because it's a max around this area. This is a local min because it's a min around this area. It's like little parabolas connected. You see how a cubic function is like parabolas connected there? That's why you call cubic splines later in calc.
The last one, it had the 7 was the highest bit and goes was the maximum.
Yes, exactly. So that last example, when the range was all the values of y less than or equal to 7, 7 was the maximum value. So that's the key we have to talk about right now. So write this down, please, in big letters right here where I'm going to show you. So right here, I want you to write this down. And it's already written, but write it like this. X indicates the location of the max or min, and the y indicates the value. And that's written in words, but I want you to write it in notation so you see that. Okay? Again, X indicates the location of the max or min, whereas y indicates the value of the max or min. These are terms you're going to hear over and over again. This is vocabulary you're going to be tested on for sure. This is the easiest way you can ever get points. Memorizing vocabulary in math. There is no reason that there's no reason that anyone should get this wrong. Because if you just put in the time, you have to memorize that. And I'm going to ask you about that on the test. I'm telling you now. Is that clear? Okay? The term min, the term max, knowing what they are. Vocabulary is a necessity. You have to know it. Okay? You can make flashcards. Anyone can do it. The math, I understand, can be tough at times. That's different. Let's go to example 3. Determine the min or the max of the following. So, to find the min or max, we need to find the vertex and determine what it is. To find the vertex, we need to find the axis of symmetry. So we work our way backwards. That's how you work as mathematicians. You think about the goal. The goal is to find the max or the min. And which one it is. To find that, we need the vertex. To find the vertex, we need the axis of symmetry. So we work our way backwards. So let's start with the axis of symmetry. Negative b over 2a, right here. You get negative, quantity is 8 over 2 times 4 is negative 8 over 8, which is negative 1. Remember, this is the x value of the vertex. But the x value of the vertex is the location of the max or min. So there's the location, that's one part. Then we want to determine the max or min value. So we go ahead and we plug in the x value into the function to get the vertex. So we take a negative 1. Alejandro, when we square a negative 1 now, it's a positive. So it's 4 times negative 1 squared, which is 4 times positive 1 there. Okay? So it's 4. This is going to become negative 8, which is negative 4. Minus 1 is negative 5. So the vertex is negative 1 comma negative 5. The maximum or minimum, which one is it? The graph must be a minimum because A is positive. When A is positive, the graph looks like this. So this has to be a minimum, and its minimum value is negative 5. The minimum's location is negative 1. As a coordinate, negative 1 comma negative 5. There's the vertex. Okay? How are we doing? It's going quick, I know that. And I'm meaning to do that, but it's because you already read over your notes and you've looked at them. So when you over break, have a little bit of downtime, if you have trouble on some of this, maybe go back and re-listen to what it says. Or what do you do in the case when you are still having trouble with something like this? What can you do to help facilitate the learning? Yeah, email me, please, okay? The first week of break, I'm going to be on that Belize trip, but obviously I'll get back to you when I get back. But I can't communicate from there. It's not going to be available.
Police trip.
Belize, the country Belize.
That's not, I thought that
There's a faculty trip in the spring break where 8 faculty members are going to do the same thing. It's just a bunch of faculty members. I mean, Mr. Linus, Ms. Coop, Mr. Blugis, Ms. Shomes, Father Hernan, or Father Paredes, Padre, Miss Baber. There's a lot of people. So, anyhow, let's keep going. Let's keep going. They're buddies?
Yeah.
No way.
Being taught to be a catch with her hope was a guy who taught me.
That's awesome. Really cool.
Yeah, they're like.
Yes.
Last one was what was the Jackson?
The coordinate was -1, -5, but the location was -1, and the value of the maximum is the y coordinate, which is -5. Okay, so it was a minimum. I think it said, minimum. Highlight that. Guys, you can use highlighters in your notes, right? You know that? You should highlight stuff. Definitely. The next example, and obviously, guys, we're going to run out of time because we have about a minute left. I did record in the other class, so if you want to just watch the end of their video, I'm going to leave their video up, obviously, because we didn't go through it. But again, there's 2 more examples to go through. You can watch them. This one was interesting, though, and I want to give you a start on it as to what it means. Don't pack up yet, please. And when the bell rings, I'll let you go. I'm not going to hold you over because it's a video. But in this problem, we have a y-intercept of 7. Okay? So that means the coordinate is 0, 7. So I really have a coordinate from that. I've got 2 other coordinates. Notice, if I take the coordinates and plug them in for x and y, so I take the first coordinate, 0, 7, I plug in the 0 for x and the 7 for y, I'll get a solution that'll give me c right away. I can just solve for c because these drop off. If I plug in 3, 10, 3 goes in here and here for x, 10 goes in for y, and I'll have, looks like 1, 2, 3 variables, right? If I do it again, I'll have 1, 2, 3 variables. So I have 3 variables, a, b, and c, and 3 equations. I can solve with a matrix. Or I can simplify the first equation. If I simplify the first equation, okay, what it becomes is just c equals 7 in the first equation. And then in the original equations, the ones that we just had a minute ago, you plug a 7 in for c in those last 2, and they become these. And then you can solve these by using a matrix. Okay? Which will give you a, b, and you have c from up here. Noticing that c is the y-intercept. So the c value is always going to be the y-intercept. That's going to be a conclusion we're going to make. I'm going to record 5 and 6 for this, because I like the way we recorded here. So I'll record 5 and 6. If you'd like to watch it, feel free to watch it. So we're going to look at now is example 5, where we have to make up our own quadratic function that is associated with the graph you see to the right here. So looking at this graph over here, I'm going to come up with values of a, b, and c that fit the graph and also make it work as far as the roots go, as far as the intercepts go, as far as the axis of symmetry, the concave up or concave down, the curvature meaning of the graph. So we have to go ahead and think about this now. So what we're going to look for is say to ourselves, first of all, notice the graph opens down. Okay, if we look at the graph here, it opens, oops, there we go. It opens down, which means that a must be negative. So a is less than 0 to start because the graph opens down. Then we look at this and say to ourselves, well, here's the axis of symmetry right here, which is some negative quantity. It's like x equals, say, -4. It doesn't matter, but some quantity over here. Okay? But it's a negative quantity, the axis of symmetry. And by definition, the axis of symmetry is negative b over 2a. But we notice there's a negative here, and a is negative from this part right here. So what we're going to end up getting is negative b over 2 times some negative quantity. Okay, 2 times some negative quantity. So the issue we get is that this negative and this negative are going to cancel, giving positives. But a minute ago we said that the axis of symmetry had to be negative. So for this to work, that means that this value here, this b value, needs to be negative. So b is negative since the axis symmetry is on the left-hand side, and since since a is also negative. Finally, we take a look at c, and to determine c, we can go back up and scroll up for a sec, and take a look back up here. Let's go ahead and delete this so we'll see back. Okay. We notice that this value here we got for c in the equation was 7. Okay, c was 7. But you also remember that the y-intercept itself was 7. So what that means is that c is the y-intercept always. And that's something that we can see by looking at this. Watch. How do you find the y-intercept? You set x equal to 0. That's what the y-intercept is, set x equal to 0. So from this, you would get y equals 7. That is the y-intercept. So it's the value of c. From that information, we could see that the y-intercept is going to cross all the way down here somewhere. Okay, there's the y-intercept. And it's definitely negative because it's below the x-axis here. So c must also be negative. Finally, there's one last piece of information. We have to remember that since there are two roots, root 1 and root 2, and they're different, the discriminant must be positive. Remember, if there was just simply one root, it looked like this, and it was tangent, the discriminant equals 0. If there were no roots on the, or no x-intercepts rather, not roots, let's say x-intercepts. If there were no x-intercepts here, the graph would be like this, and the discriminant would be negative. But because there are two distinct real roots, the discriminant is positive. So we need to find values for a, b, and c that are all negative, yet keep this to be positive. So what I would do personally is pick your a and c values so you get this quantity here. And then from there, you can pick the b value that'll make it work. So I picked -2 and -3 for a and c. That's what I chose. So let's see what you get. And these are going to make positives because they're both negatives. 4 times 2 is 8, 8 times 3 is 24. So that means that whatever the quantity b is squared needs to be bigger than 24. That's why I chose -6. If I had chosen -5, that would work also because it would have been 25 minus 24. But since I chose -6, it's 36 minus 24, which means it's still greater than 0, the discriminant. So -2x squared minus 6x minus 3. Again, all of these criteria have been met. Alright, let's take a look at example 6. So example 6 asks us the following. Determine how many times the parabola intersects the x-axis, the line y equals 7, or the line y equals 10. Well, if we want to see how many times it intersects the x-axis, we just can look at the graph of it, really. But we say we can't graph, we have to show algebraically. Well, the x-axis is where the roots are. The roots are setting this equal to 0. So that's what we'll start by doing. Okay? Now, the x-axis, keep in mind, is really the line y equals 0. And that's something most people forget. And here's how you know. All horizontal lines are y equals, but this goes through 0. So this is the line y equals 0. So we want to know when the line y equals 0 is the same as the parabola, or when they intersect with each other. So because of that, all we have to do is look at the quadratic formula, or simply look at the discriminant. If the discriminant is positive, we have 2 intercepts. If the discriminant is 0, we have 1 intersection. If the discriminant is negative, there are no intersections. So looking at the discriminant, we get b squared minus 4ac. That's this quantity right here. And that's going to give us simply 84. Okay, because it's a negative makes it a positive. So we have 36 plus 4 times 3 is 12. 12 times 4 is 48. Okay? That will give us 84. So since the discriminant is positive, there must be 2 intersections, or there must be 2 roots. Now, let's go on to the next part. You can go ahead to the next one and look at it and see, all right, well, this part says, how many times does it intersect with the line y equals 7? Y equals 7. Well, the line y equals 7 is somewhere up here. We want to know when it intersects with it, or pretty much when it's equal to. Intersect means equal, remember that. So you start by saying 7 equals negative 3x squared minus 6x plus 4. So instead of the y equals 0, where we put a 0 in there, now we have the line y equals 7, so we put a 7. But then solve for it, so subtract. Subtract 7, we get this. And looking at this, b squared minus 4ac, okay, b squared minus 4ac for this quantity turns out to be 0. Okay, and you can see that because this is 36 minus, oops, let me go a little further down. This is going to be 36 minus 36. So 0. When the discriminant is 0, we have a graph that looks like this. So here's the line y equals 7. And the graph has got to be tangent. Okay? I don't necessarily know the other stuff. I mean, I do, but I'm going to assume I don't. But I do know since the discriminant is 0, there's only one intersection. So it's tangent to line y equals 7. And this holds true because I still have two answers for the line y equals 0 for the x-axis. And I know it opens down because a was negative in this problem. Okay? A is negative 3. The last part is when does it intersect with the line y equals 10? Well, just by inspection, it's never going to intersect with that line because it's above, right? Here's the line. Since this line is above y equals 7, and since it opens down, and if it intersects the line y equals 7 once at a point of tangency, right here, it's not going to intersect up there. But let's prove it. So we'll set the equation equal to 10 now. Adding the 10. Or sorry, subtracting the 10. I apologize. And now what we can do is take a look at the discriminant for this. B squared minus 4 times A times C is equal to 36 minus 72. Right? 4 times 2 is 12. 12 times 6 is 72. Which is negative 36. Which means that there are no intersections. Okay? When it's a negative answer, there are no intersections of the parabola and the line y equals 10 up here. Okay, this line. And we know that just by looking at the graph, but this proves that there's no solutions or no real solutions, which mean that there are no intersections. Remember, the solution to an equation is the location of the intersection on a graph. Okay? So that's our last point to make there. Let's quickly just take a look here. Again, no intersections. The homework for this is right here. Again, please watch these videos if you need more help.